So thank you, and thank you very much to the organizers. It's a great pleasure to be here. It's been a fantastic conference so far. I hope I don't lower the level. I've only written one paper with Guy, so I used it as my file name for this conference. You didn't see it up there when we loaded it on. When Guy spoke about this work many years ago, it came out like this on his slide, and Gilles Pizier was the first to remark that this was a case of me swallowing whole an entire. Un trait là, oui, c'est ça. So in my case, it also doesn't work this way for some reason either. Guy we've talked over many years, and he was generous enough to be the one, the sort of the inspiration for me joining this wonderful group that has been working on this. And I think maybe the only reason was that I'm separated in the alphabet by one person, so he doesn't have this problem of being swallowed up. Otherwise, maybe I wouldn't have joined the group. Anyway, it's been a great pleasure. We've been working since around for at least 5 years on this, and we finally have a number of things that I can share with you. So what I'll be talking about is localization of eigenfunctions via what we're calling an effective potential. And it's joint work with Doug Arnold and Guy, and Marcel, Filoche, and Svitlana, who just spoke this morning. So the kinds of eigenfunctions we'll be talking about are eigenfunctions which the main area that we're interested in is eigenfunctions associated with what's known as Anderson localization. So there's a very curious situation in mathematical physics where, and I'm just going to give you it by example here, you have a Schrodinger operator, Laplacian plus V, and you can simulate this on an 80 by 80 square, and now the potential is going to be random. So we pick this V to be constant on unit squares, so it's piecewise constant, and the values will be uniformly distributed, say, in the interval from 0 to 4 in the numerical experiment that I'm going to show you, and they're just identically distributed independently, all right? So let's just take a look at what the first eigenfunction looks like here. So this is for periodic operator, and here it is, all right? So you could agree that this is localized, I think, okay? So that's a very curious phenomenon and very important in physics. And so you can ask yourself, this thing is random, so that it could pop up any place, obviously. And the first question that one can ask is, where is it going to pop up? All right? So where is this first eigenfunction? And this question was answered in a certain sense by Marcel and Svitlana, Filoche and Mayboroda. You solve an auxiliary equation, LU equals 1, which means that you essentially put uniform pressure on the whole business, and the place where it vibrates most, the place which responds the most, the largest response, is the place where that eigenfunction is going to be. Okay? So, this doesn't look completely that surprising initially. If you of course know perfectly well, first of all, we have one equation here, we have one equation there. You know, you could solve one, it sort of looks equally complicated. And of course, U is just the superposition of the eigenfunctions. When you have the bottom of the spectrum, this denominator here is the smallest number, so that should maybe be the biggest one. In the Dirichlet problem, even it's positive. This would happen to be with periodic boundary conditions, but in the Dirichlet problem, this is positive, so this inner product should be the largest in that case. So yeah, the first one should be at this spot. This is perfectly reasonable. But what Filoche and Mayboroda discovered is that the pattern goes way, way, way deeper than this. It's really pretty astounding, actually. It's much, much more associated. Somehow there's a lot more in this function u that talks to all of the eigenfunctions, or anyway, let's say at least half of them. Okay? And this really matters because you're interested in these physics problems of the whole array of the eigenfunctions, the whole eigenfunction distribution, or at least the bottom half of the spectrum. All right? So I'm just going to show you one numerical experiment on this same data that I showed you before that shows you how much this u, how well this u can predict the other eigenfunctions. Okay? So this is not, okay, so here's another picture. I hope you can see it. Here's the view from I did a side view before, this is the top, and it's color-coded by the intensity, the how high the eigenfunction is. And here's the one that you saw before, now viewed from the top, the first eigenfunction. The next maximum is over here, the next one is there, the next one is there. Okay? So of course, again, you might think that this is just the superposition of eigenfunctions, but that sum doesn't converge very fast. The denominators are actually rather slow, so there has to have been a tremendous amount of cancellation in the oscillation of the entire sum for this somehow to pick out all of this stuff. And the level lines turn out to be just perfect. It's predicting the shape, actually, of these eigenfunctions. And it goes much, much, much higher. I've just shown you the first 4. It goes all the way up to filling this whole region here with eigenfunctions. Okay, so at least the first 40 are easily explained. So that's a little mysterious, and that's what we want to discuss here. So the start of our study of this to try to understand why this is working just amazingly well was to do something nonlinear. So this is a linear equation, but we're interested in the shapes of eigenfunctions, and the shapes of eigenfunctions, or the level sets of eigenfunctions, aren't a linear problem. They're a nonlinear problem because they don't, the level lines don't satisfy a linear equation. So there's no reason why you should just use linear ideas. So this is the sort of simplest possible nonlinear idea. We're going to study, instead of the eigenfunction, the ratio of the eigenfunctions of this function u, which Filoche and Mayboroda called the landscape function. Okay? So this is a standard trick which goes back very, very far to look at ratios of functions. And the lucky thing here is that it just so happens that in the context that we're considering, when you have a positive bounded potential, u is you can solve the so-called LU equals 1 landscape equation, and you'll always get a positive u out of it. So you can divide by it, that's legal. And then you could just look at how the equation transforms. What's the equation for the eigenfunction versus what's the equation for this transformed eigenfunction? So what is it? Well, you just calculate. You have to conjugate the operator. You have to multiply and divide by u. That's all that's going on here, and here's the answer. Now, this is a standard trick. That's why this thing works nicely. The potential V disappears from the right-hand side. So that's the key thing, and this is the standard thing that one does with ODEs. When one studies second-order ODEs, this is one of the standard tricks. And instead, in place, we have the reciprocal for the potential. We have some other second-order operator. So what's happened here is we've got the energy term, the kinetic energy term, and we've got the potential energy term. And now we've traded it somehow so that there's a different potential energy, kinetic energy here, and there's a different potential energy over there. So we're just looking at this in a different coordinate system in some sense. So what can we get out of this? Well, we gave it a name. It's the effective potential. It's the new potential that we got when we started with V and we ended up with 1 over u. And if you notice, the principal symbol of this operator is just the same as the one that we had before. And actually, so this is a weird compromise here, and it takes a long time, and we're not fully through with understanding this. But this extra energy term, which will matter to us, is not so far from the ordinary Laplacian because u is fairly smooth. It's a lot smoother than v was. V was this very discontinuous thing, but u is a little smoother. So it's not ridiculous to make this approximation of the top order term to commute the divergence and the u squared factor. All right? So here's the principal symbol. And so one thought that one has that comes to mind is that maybe you should try to use the Weyl law on this symbol rather than on c squared plus v. So the Weyl law is the law that tells you how to count eigenvalues. This particular 1 over u is really good at identifying things at the bottom of the spectrum. The Weyl law is something which works only at the high end of the spectrum. It has to do with pure frequencies e to the I x dot c, the trivial frequencies which divide space up into equal boxes. But this is somehow connected to the bottom, so maybe it does better at the bottom. So it's basically the opposite of the Weyl law, but we're going to try it out. So let's see what happens numerically when we do that. So you run it with, so we'll just do it with one-dimensional experiments. And here's one of the first ones that we did. You have a potential with minus d by dx squared plus v. And what kind of potential is it? It's uniform between 0 and 1. Okay, so on 512 unit intervals, we have a long line, which is 512 long. And on each unit interval, we put a number, and it's a number between 0 and 1 uniformly at random. And then we compare the actual eigenfunctions, which is the black line here, the actual count according to energy level of the eigenfunctions. And this is the number of eigenvalues less than that energy level, and we see what that is. And then we compare it to the stupid line, which is the blue one. That's what you would do with the potential V. That shouldn't work. It's garbage at the bottom of the spectrum. Okay? It's going to be asymptotically correct when we don't care about it anymore and it's obvious at the top end. It's going to be fine. But it's ridiculous, okay? And then look at this one where well, this W is 1 over U. What you do, and when you do the counting with the symplectic volume in this one with our guy. So that's the dotted red line. Okay, and what I want you to pay attention to especially is look at how it captures the start of the spectrum here. It nails it. This is what's totally useless here, but at the beginning, it's actually already right on the nose. Okay, so this is a purely phenomenological numerical thing. So let's just take a look at it. Instead of uniform distribution, let's do it with Bernoulli. Let's do it with just zeros and ones. Okay? Let's see what happens. So here's Bernoulli. Again, the blue line is stupid and ridiculous. Okay, we know exactly what it is. It's half zeros and half ones, right? So, right? So that's what you get apparently. I mean, if you do the numerics, that's pretty easy. You could do this analytically, not numerically. And here's the actual on the black line, and then the red dotted line. Look at where it starts. Okay, and you can zoom in on this and you can see that it's starting pretty well. So this was pretty thrilling for us to see that this was actually, this meant that this was really something, okay? So now, you know, maybe this is some kind of probabilistic law and we're just, there's a phenomenon here and there's another phenomenon here, and it's just that both are being caused by the same thing. It's not absolutely clear, actually. We don't know that for sure even yet. But anyway, you can also try it in a deterministic case. So we'll do one more case. We'll do the case in which it's not IID, it's just alternating zeros and ones. Okay, just periodic alternating zeros and ones on the entire 512 grid. So again, the blue line is going to be the same because even though they're reshuffled, it's just the same counting law, because that's the distribution function of half zeros and half ones. So let's take a look at it. See, the blue line is the same, and this one is very well organized because it's a very straightforward periodic thing. Now look at our red guy. So you know, this has got to be something, this phenomenon, right? So this is, okay. But even though it's not a theorem, Marcel and Svitlana were working already on trying to understand numerically using their landscape function, the function u. They were trying to understand the behavior of LEDs. It turns out that at LEDs, the way they work, you know, they shine very bright light. The way they work is that they light up in various spots very, very brightly. And the important thing is to control that they get very bright in certain spots. So exactly this localization is part of the phenomenon. Now, it's much more complicated than that. It's a little like the story that Jafar was telling us about earlier this week. You know, there's also some physics involved, and there's also some engineering involved, and so on and so forth. But they were able to use this idea of just counting, and that a piece of their algorithm, and they showed that they could speed up the algorithms that simulate the performance of these LEDs by a factor of 100 to 1,000. And in our numerical experiments, we've seen extremely similar things. If you actually wanted to calculate the eigenvalues by the optimal things that are known, it took us 2 days to make sure that our predictions were actually correct. We could calculate in 2 minutes from the landscape function what the eigenfunction distribution is, and then it takes us 2 days of calculation to check that it matches on large examples.
What about the eigenvectors themselves?
Well, so we're going to talk about the eigenvectors. And indeed, so there's this question of the localization of the eigenvectors. But anyway, this is where there's been some success that actually helps in a real engineering problem that maybe will save us some energy someday. Just happens. So this is pretty fast to get from theoretical math to a real practical application. Okay, so this is very neat. And what I want to tell you now is that we have the beginnings of an explanation for a strong connection between this effective potential, which is sort of the right perspective of the Filoche Mayboroda landscape function, which is the function u. So the reciprocal is the right point of view. with some actual theorems associated with it. Okay, so that's what I want to explain. So in order to explain theorems, I want to mention just one other thing that is standard in the theory of Anderson localization, which is the first example that I gave. There's a prediction, and it's proved in one dimension and not so much, not as much in higher dimensions. There's a lot of unsolved questions, which is of so-called exponential localization. The eigenfunctions have a specific quantitative way that they die off, which is exponentially. So we do have a theory in mathematics of exponential localization of eigenfunctions, and so let's look at that theory and just review it for a couple of slides. Oh, I forgot one slide. Crumb bum. So, you know, after this stuff, we've shown, right, so this addresses another little question is it the sample? So in other words, are we just having a probability law thing and we're just reading off something like, you know, the standard deviation and something or other else of two statistics of the same phenomenon, and are we just watching that coincide? Or are we actually doing something which, relative to the specific sample, is telling you something different? So this is some numerical evidence. I forgot I stuck this slide in. I apologize. So you can also predict the eigenvalues by counting the minima of the reciprocal. So remember, the first one I found was the first eigenvalue. The second was the second eigenvalue on that first picture. I went through 1 through 4. Now we're going to go through more of them, more of these eigenvalues, and we're going to see whether we have this consistency that we get the eigenvalues in order and also their sizes. And we're going to do this not just with one simulation, but with 64 simulations to see what it is. So now, suppose you're looking for the 25th eigenvalue, and suppose you read it off from this really fast algorithm which calculates this 1 over u, and you take its 25th minimum. I claim that this is how it will match on the 64 simulations. Each of those dots represents one of the simulations. So sometimes the 25th eigenvalue is up here, sometimes it's down here, but our prediction is working all the way along. Okay? And here's the first one, which is even tighter, and it's giving up around the 50th. This is about half. Here the Vmax is 16, so the range of eigenvalues is between 1 and 16, or 0 and 16, and we're not getting up to halfway, but we're getting, you know, and it is getting a little worse as we get to the middle of the spectrum. Okay, but it's doing pretty well, wouldn't you say? All right, so this is not Weyl counting. It's some other predictive thing, but again, a fast predictor. Okay, sorry. So now I can get into the theory. So going back. So now we're going to talk a little bit. We've talked about eigenvalue distributions. We actually will get back to that at the very end of the lecture. But right now, I'm going to be talking about the shape of the eigenfunction and the exponential decay in order to get some relationship between 1 over u and what we're seeing. So let me remind you of something trivial from ODEs. If you have a super solution to an ODE here, and you know it tends to 0, say going to the right, going all to infinity, then it has this exponential decay. Why? Because you compare it to the solution where this is equal to alpha squared psi, in which case darn it. In which case it's exactly e to the minus alpha x squared. We eliminate e to the plus alpha x because of this decay property in infinity, right? There are two solutions, and only one of them is picked out. All right, so this is trivial ODE theory, and the n-dimensional theory of this is sometimes called classical confinement, and so let me just remind you of this. If you have a Laplacian plus a potential in Rn, and you have an eigenvalue level, then basically, so I'll draw a picture of it. you have a potential well. So this is V. And then you have a level, which is lambda. And the eigenfunction wants to live down in here, right? And it tends to die off where there's a potential wall. This is called classical confinement. It's not perfect. It doesn't stay there because there's some quantum effects, but it's mostly there. It's exponentially small, far away. All right. So this gets proved classically using the following trivial inequality. All right. This inequality is trivial. Gradient f squared is a non-negative quantity. And so this is true, all right? So that's very helpful. That better be true, all right? Okay, so how is it used? Well, so it's used, it's called a form bound. It's a lower bound in the sense of L2 on the operator with this weight, but not on all of space. You have to restrict to the place where W is strictly positive here. And so the function that I'm considering, so this is a very important part of the notation here, is that the function W is this function. It's flat, and this is its zero level, and then it's going up. So W is 0 here, and then it's going up. And where it's positive, that's where the eigenfunction doesn't want to live. And of course, it's relative to the level. We're going to move the level up and down, lambda, up and down. But anyway, this is the excluded zone for the eigenfunction. So how is this proof? How are we actually going to prove this decay? So again, this is the key inequality here, is that you have this lower bound with a weight here, and the W is non-negative. I didn't say that, but we're only restricting to W positive anyway. And then the theorem was proved by Agman, and he introduced this so-called Agman distance. So the distance is just the distance with W being the metric, essentially. So you take the square root of W, you measure distance with respect to that, and then you measure the distance from the zero part, that's this flat part, and all the parts out here, it's getting farther and farther away. It's harder and harder to get farther away. If the potential is increasing, this distance becomes enormous. Okay? And then the theorem says that if you have an eigenvalue, an eigenvector, so obviously this is the decay at infinity that you need to get started, then in fact it decays exponentially fast with exactly this rate here within epsilon, this exponential rate. And I just remind you, the ODE story is the case when W is alpha squared, and the square root of W is alpha, and this is alpha times x, okay, because I've integrated it on the whole length. Okay, so this is the standard theory of classical theory, if you like, from the point of view of mathematicians, although it was rigorously proved by Agman. So we're looking for this, and remember, this is the arithmetic that we did before. We conjugated the operator, and we came up with this new version with this 1 over u here. So let's see how this works. I'm going to take the form, and I'm going to look for the form bound. Well, this formula is the same as this identity here. I've changed my quadratic form associated with the operator to a different one with a substitute kinetic energy here and a new potential energy over there. This is just an identity. This is just an equation. And now I'm going to use the same trivial, yikes. I'm going to use the same trivial inequality. This is a positive term. And so, lo and behold, I have the same inequality. I have the inequality that fits into the Agman theory. There it is. It's the same one, but I've just replaced V by 1 over u. Okay, so that's another reason why so now we really know that we have what we're going to call the effective potential. We have this thing which plays the same role as V, and we know that it satisfies the right form bound on the nose with the lambda. So we have every hope that we'll be able to prove the same thing that Agman did. All right, so I guess I said that here. We're expecting, and we will prove some kind of exponential decay. Okay, so there's a lemma, and the lemma actually is the identity that I just did. But now there's one extra trick that I want to introduce to you, which is trivial, which is that trivial but helpful, which is that we actually need this identity. We're gonna prove this identity by a different method. We already proved this identity. I wrote it down for you. It's just a calculation with change of variables, with a conjugation by u. But actually, we're going to prove it by a better method. So what we're going to do is we're going to prove this identity by plugging in the equation LU equals 1 in weak form with this test function. So if you do that, you get this equation, which turns out to be the same as that equation. So this is the trivial proof, which is better than the other proof because it doesn't have any integration by parts. It doesn't require any smoothness. It's a much more universal fact that this is true. So that means that we're going to be able to dispense with smoothness in all of our discussion. So we get incredibly lucky here is that all the proofs are easy. All right, so that's the lemma. And now I'm going to build up to state the theorem. I'm going to actually tell you all the notation that gives the theorem. And then the main, just to anticipate, the way that the theorem will be proved is just by plugging in the right f here. That's all we will have to do. Okay? So we just plug that into the identity. All right, so let's build up the theorem. So remember, we have this weight. Now I'm going to have to, in order to state the theorem properly, I'm going to have to give myself some room. There's the well, which is the level lambda, but I'm going to give myself a little bit of room delta above the well. Okay, so I'm going to give a little space around it. And now I'm going to take Agman's distance associated with this weight, and then I'm going to take the distance to that well, which is maybe a little larger than the one that I had, and I want to stick with this notation here. So that's the analogous to what we did before. And now I can state my theorem. The theorem says that if you have an eigenfunction, right now I'm on a compact periodic manifold. Later on we'll see that we could do this on general manifolds. So here's the statement. You have this exponential weight, which is exactly this Agman distance. You have the ordinary gradient. We've gotten rid of u from this expression. There's no u here. This is the ordinary gradient. This is not v. This is the maximum of v. This is just a constant. This is a totally transparent quadratic expression here. And all of the information is in this weight, which is exponential, exactly designed to be associated to that weight there. All right? And this is the region where you can do this. And then on the other side, I claim I've got a completely balanced expression, which is just the L2 norm times the appropriate constant. This expression is gathered together to show you that it's the same units as that one. This is also in balance. The maximum of v, the band of frequencies where you have eigenfunctions is between 0 and v bar, the maximum. And the delta is the amount of error that we have in the same units, so that's also a unitless quantity. And then we have an absolute constant. So this is a universal statement. It's independent of scale. It's independent of everything. The actual number here is a little smaller than 100. This is a real number here, and the actual number is something else, which I'm not going to show you. And we haven't optimized this number, but it's less than 100. I promise you that. Okay? So this is the theorem. So again, so let me tell you the proof. The proof is, I already told you, is you just plug in the right test function. It's the exponential to the appropriate power times the cutoff, and the cutoff is just h for most for the transition between 0 and 1, and then constant 1 from then on. So for h greater than or equal to 1, it's just constant. Okay? And then you have to use this Agman type bound, which is the gradient is related to the weight, which is natural for metrics. This is true for, I mean, it's really not original with Agman, but it's an important part of his proof. So now let me just add, this is so easy, this proof is so easy that it generalizes to closed C1 manifolds with C0 metrics and L infinity densities, and there's no change. You can even do the Neumann problem with bi-Lipschitz boundaries. It's the same proof, it's the same concept. That 100 works in all of these contexts. There's nothing to do with smoothness here. This is true on arbitrary manifolds, say, with the same constant 100. It's just all matched. Okay, so that's the proof. And I've stated my first theorem. So let's go on now. So what are we going to do next? Well, we've established the exponential decay. Now I want to get a little bit back towards explaining why the eigenvalue distribution worked correctly. And we're going to get sort of halfway there in our explanation. And I also want to explain how close we can get to diagonalizing the operator. So at the same time, whenever you do actually prove things about eigenvalue distributions, you really implicitly have to almost diagonalize an operator. So you can't really do it without getting your hands dirty with something to do with the eigenfunctions themselves. Oh, but I forgot. There's one other thing I have to tell you. Yeah, right. Sorry. Does the theorem have content? So that theorem was actually a little bit tricky, right? It had all this stuff in it, right? So does it have content, right? I mean, it's implicit. Everything is hiding inside of whatever this h is, and there's this delta, and the h depends on the delta, and so on and so forth. So of course it's all intertwined in there. So it's not so clear that there's even any example in which this theorem has content. Yeah, pretty important point. So let's try to address that. So here's a numerical example that shows you that when you produce u's at random, they actually, the theorem applies to them. Okay, so here we have just the real line with this very, very long interval, which is 2 to the 19th long, with v chosen uniformly at random in the interval 0, 4 on unit intervals. And then what you discover is that there are about 17 Weyls when you perform this for to see what's happening just with the ground state. So, and the Agman distance between the Weyls is about, so you can do this by doing powers of 2, you can actually get the power law of this, and you can say this very rigorously, that this is approximately the separation between the Weyls, almost surely. So this is how big, this is basically what I'm saying is that when I did this process, and I'm trying to identify what's happening with the ground state, I'm gonna have to cut it, and I'm gonna find the ground state is maybe here, maybe there, maybe there. I won't know exactly where it is. So the level of accuracy of the theorem is that instead of telling me the ground state is in just one place, it tells me that it's in one of 17 places, which is a lot smaller than 2 to the 19th, okay? So it's not so bad, but it's not all the way there. Now, there's a good reason for this. So the theorem for sure has content, and as t goes to infinity, it's getting better and better, okay? It's asymptotically fantastic. You've got this exponential which beats by a mile the algebraic powers involved in the rest of the estimates. But we, as I say, we don't prove that the deepest well actually wins, which is what a more sophisticated theorem would do. In order to do that, we will need an extra hypothesis because it's false in general with the hypotheses we have. You also need to know that the wells are different. If they were all the same, indeed, they would share energy and you would have resonance. So there has to be another hypothesis. And of course, that happens to be true for these Anderson models. But of course, you could change the U and you could make it so that it's not true. So in other words, we didn't fall into a trap of proving something inconsistent in mathematics when we proved our theorem. Anyway, okay, so that's a good sign, not a bad sign, that we're not all the way there in explaining this phenomenon. Okay, so now I get to the last general subject, which is the so-called approximate, what I would call the approximate diagonalization. So here again, we can actually prove a theorem, and it's going to be some work just to formulate what the theorem is, how the theorem is stated. So again, I have my wells, and I'm going to choose a threshold. So now I'm trying to count eigenvalues and understand eigenfunctions up to the level mu bar. And I'm going to do all of the ones below mu bar. All right? So I form that well. Well, there could be a lot of pieces to it, and I'm going to break it up into those pieces. Now, the pieces are usually just connected components, but sometimes by accident there are a couple that are right next to each other, and those you just want to stick together, because the whole point is that we want the distances between wells to be huge, maybe t to the 1/5 as in our numerical example. So this is the model that I have in mind. Was I took these wells over there, I broke them up, and then typically there should be a reasonable separation between them. And then I just surround each by the largest thing you can, which is I go halfway. The distance between EL and this surrounding domain should be S over 2 so that they don't overlap. Right? So I trap each of them in an Agman ball of radius S over 2. And now the claim is that we can compare, so now we're going to do our diagonalization. First, just notation, we'll let the projection, the orthogonal projection onto the eigenfunctions of L with eigenvalue in this interval be denoted by capital Psi. And then we have the Dirichlet eigenfunctions, there's a little typo there, of each of these domains be listed here. So these are the so-called localized ones. They also have exponential decay. They're really supported in this tiny little well in the middle, and then they spread out, and they're very, very small. And then they're 0 on their big boundary at distance S away. Okay, so these are the nice localized eigenfunctions, just one per well, and then of course they go up in frequencies. And now this spectral projection is the projection onto the direct sum of all of those families. They're disjoint, so they're completely disjoint parts of space. So with those two notations, I can state my theorem. So suppose you have a phi, which is one of the localized guys, and its eigenvalue is less than this threshold. Then its projection onto the eigenspace of the original eigenvalues is reasonably small. So what does reasonably small mean? Well, so we need this band. We can't trap it in a single eigenvalue. There's always this uncertainty as to the resonance. If the eigenvalues are identical, we can't possibly distinguish. So we need a band, and it's quantitative. And then here, instead of this ratio to the first power, we have it to the third power because the proof is a little more complicated. And then we have a specific number, and this 300 is a real number and works for all manifolds. And then we have this very specific thing, which is exponential in the examples that we have, if we have a suitable landscape, a suitable 1 over u. This is a nice number, and a lot is a factor that kills this algebraically sized object here. And then we have exactly the same thing the other way. If you take an eigenfunction of the original, then it's trapped in a spectral band of the phis with the same constants. So I guess the last thing I need to tell you is about the proof. And the proof is the following. You just cut off the eigenfunctions inside each of the domains, and you see how much error you have. And our first theorem, the exponential decay, says you can take this cutoff so that it's just sort of at the edges of omega L, so that this R is contributing an exponentially small amount in error. So this is compactly supported, so it can be compared to the phi eigenfunctions because it's trapped inside of the 1 omega L here. So you just cut it off, and then the error is estimated. So now how do you estimate the error? Well, I guess this is one subtle point which I sort of didn't emphasize enough. We don't just get exponential decay of psi, we also get exponential decay of its gradient. So we have exponential decay of the H1 norm at a large distance, which means that when we operate by L, the error we're going to make is in the H minus 1 space. Right? We differentiate twice, and we get. So we've controlled this very, very well exponentially in the ordinary Sobolev space, and so this happens to be the dual space, which is very important. So we're allowed. This is the norm in which we've got to make this estimate, and this is the estimate that we get. This is another one of these explicit numbers, which I threw in an e squared for the heck of it. This is like 132, so I didn't want to put down a number. Anyway, so this is the bound that you get, and there's the same thing the other way, and then you just put this all together and so then our last corollary is the level at which we actually have honest counting. So the last corollary is that if up to this sort of exponential amount, we can allow n to go up that high, and then the lambdas will coincide with the eigenvalues, the localized eigenvalues within plus or minus delta. So the counting does work. It isn't perfect. We're off by 17 in this the way this theorem goes. To improve it, we'll have to do better with this exponent, which has to do with, again, an extra hypothesis resonance. So we're not there yet, but we have the beginnings, and this is a theorem that actually has content, even though it's not the full story. It's not as good as what we see. It's telling you what's happening at the bottom of the spectrum. Okay, so just to review, we introduced this beautiful effective potential. What we really know numerically, and we wish we knew theoretically, is that the eigenvalue distribution of the bottom half is well predicted by it, that the localization, the exponential decay, it just follows from reading off this, and that one gets an approximate diagonalization of the operator from that. And it was Guy who got me involved in this, and this theorem is merci à Guy.
No, I was wondering if you can prove some estimates about the sensitivity of the localization of the eigenfunctions depending on the potential V. So if you perturb a bit V, because it reminds me some work on semi-classical analysis where there is some tunneling effects, and if you perturb V somewhere a little bit, it can completely change the localization of the eigenfunctions. And I think it's the next step after those estimates.
Yeah, so a lot of the work not just in math, by the way, also in chemistry, people are always doing perturbation theory of operators. What they actually do in practice basically for all quantum mechanical systems, as far as I can tell, is they've already measured some particular case. And they don't know what the details of that one are, but basically they're going to perturb it by something else. And those computations they can make. So this one they get numerically or experimentally, and then they make their predictions based on this. So this is like the tool for actually making serious predictions. This is the way that it's done in experimental chemistry, for example. So I mean, this is a valuable question just basically in every possible subject. And you know, because we have a new coordinate system, because we have this 1/u perspective versus v, we could ask for, you know, how perturbations of this affect this. And that's an extremely valuable issue. I mean, I can't say it's an excellent question.
Let me say something here. Many years ago, and this relates to stuff with V and various other people, even I looked at the homogenization problem, which means that you have a family of potentials which are random, like the ones that David described, and they have a weak limit in the sense that you get sort of asymptotic behavior of the potential in a weak sense. Now, none of those operators have a limit which is a weak limit. I mean, if you have a divergence Laplacian, another Laplacian, you want to know what is the effective potential that corresponds to it. What we discovered is that this landscape function, right, 1/u, which is it was a t of 1, 0, where t was the Green's function of the operator. So if this function, this controlled function, landscape function, had a weak limit, it was a necessary and sufficient condition for the operators to have a weak limit. And you had that. We never published it. It was published by Sijue Wu in a paper for the parabolic situation. But the issue is, how is the spectral theory dependent on those potentials? And that's exactly what we were doing. We were doing this perturbation series and renormalized it to become weakly continuous, essentially. That was the story. This was, I don't know, 30 years ago.
So just to mention something, another connection in a similar vein, the people who do Anderson localization, so this probabilistic part is somewhat unsolved, especially in dimension 3. People are interested in a phase transition. The way that they have gotten at it in the past is very closely related to what Rafi just said, is they look at Green's function and the main of the operator, and in fact the resolvent. So it has dependence on the eigenvalue. And then what they're interested in is exponential decorrelation as x and y get far away from each other, and that's the symptom of Anderson localization. That's the mechanism for proving it. Is detailed behavior of this resolvent function. And there's the opportunity with this other function of doing something similar. And the advantage that the effective potential has is that there's no longer this parameter lambda here, which actually is also the complexity which gets, which one beats when one computes the spectrum all at once just from this one function. You don't have the spectral distribution. I mean, it's all somehow hidden inside of this operator and can be quickly deduced from it. So there's a fair chance that this helps. Anyway.
Are there other questions? No. So let's thank again the speaker.